This is The Guardian.
Humans are obsessed with getting old, or more precisely, staying young. And while there have always been those willing to hawk anti-aging elixirs and sell us dreams of long, healthy lives, so far the quest for eternal youth has been a dead end. But now science is beginning to catch up.
This is an exceptionally hopeful time. This is the first time in human history where we have a pretty good idea what some of the mechanisms driving aging and the diseases that accompany it.
As you can imagine, this has turbocharged our fascination with longevity.
Aging is 80 to 90% the cause of heart disease, Alzheimer's. If we didn't get old and our bodies stayed youthful, we would not get those diseases.
We have discovered several genes in our centenarians. If we can imitate them, if we can understand what happens to them, we can create it as a drug.
I've looked at my blood biochemistry and I'm actually now younger and healthier than I've ever been.
And even though they say one thing money can't buy is time, that's not going to stop Silicon Valley billionaires.
The only objective we have is don't die.
Don't die.
It's that simple.
Most of us aren't going to get infusions of young blood or take hundreds of supplements a day. But beneath the hype, there is something troubling happening. The global population is aging. By 2030, 1 in 6 people in the world will be aged 60 years or over. Today, a child born in the UK has a more than 50% chance of living into their 90s. That doesn't mean they'll be healthy when they get there, of course. So how are we going to cope with the increasing burden of old age? Can we put off our last decades and make them more youthful? These are big questions plaguing the best scientists, doctors, and economists. So across this mini-series, we're boiling this all down to ask, what is aging? Can we put it off? And how can we do it well? I'm The Guardian science editor, Ian Sample, and this is Secrets of Aging, Episode 1. What makes me old? To answer this big question, what is aging, I got on the line with Richard Farragher, Professor of Biogerontology at the University of Brighton. He said we should start with an observation by an early 19th century actuary called Benjamin Gompertz.
What Gompertz observed was this, that what we call extrinsic mortality, so your chance of dying being hit by a lump of concrete or being run over or things like that, tends to be fairly constant with time. But in humans and most other species, you see an exponential increase in the chance of an organism dying or becoming sick the longer it's been around.
That is your intrinsic mortality.
So to give you a sense of it, when you're 20, your chance of dying of an infectious disease might be 1 in 10 or 20 million, so roughly equivalent to your chances of being struck by lightning. By the time you're 85 or 90, your chance of dying from the same infectious disease might be 1 in 700, 1 in 750. So I hope you can see the increase in the chance of dying over time is massive, and that is aging.
Physics dictates that we all experience the march of time. Every living thing might age chronologically, but not everything gets older biologically speaking.
There are a number of very rare, what we call non-aging organisms. If you've ever had clam chowder, you've probably eaten an organism called Arctica islandica, and that's a non-aging organism. And the clams in your bowl of clam chowder were probably older than you are. The oldest Arctica are so old that Shakespeare could have had them in a bowl of stew. And the reason they are so long-lived is that they have a very low chance of death, and that appears to stay fixed over very long periods of time. But again, the bowl of clam chowder is a good example of this. Being non-aging doesn't mean you are immortal.
It might seem obvious that the older we get, the more likely we are to die. But the question of why, what's happening in our bodies that makes this true, is actually a very complicated one. Scientists like Richard are on the hunt for what are often called aging hallmarks or mechanisms, the things happening inside us that drive us up the Gompertz curve.
When we talk about aging mechanisms, we talk about some physiological process that ticks three pretty straightforward boxes. The first one is the process has to be present in intact bodies, because if it's not present in a body, it can't make a body age. If it's present, it needs to be capable of exerting a physiological effect for good or ill. And that would distinguish an aging mechanism from the kind of thing that you'll often come across, for example, if you watch a forensics or archaeology program on the TV. If you section through a human tooth, you will see that humans lay down an annual dentine ring, like the ring of a tree. But those rings don't do anything. The real nub of an aging mechanism is that speeding that process up will speed up aging, and slowing that process down will slow down aging. And there are quite a number of these hallmarks known now, 9 or 10, and I am sure that other hallmarks remain to be discovered.
Richard's research focuses on one of these hallmarks, something known as cell senescence, when cells stop dividing and then begin to cause trouble.
The way this works is as follows. The normal course of your life, you lose cells. That loss has to be balanced by cell division.
Each time a cell divides, something happens to our chromosomes. At the end of each of our 23 pairs of chromosomes, there are structures called telomeres. These are small sections of DNA repeated thousands of times over, and they form a protective cap like the tip on the end of a shoelace. These telomeres are important for allowing our cells to divide safely, but whenever they do, the telomeres get shorter. This is a hallmark of aging. Another is genomic instability, the build-up of mutations and damage to our DNA as it replicates and we interact with the outside world. These changes can prompt cells to become senescent and exit the cell cycle. You don't want to keep making broken versions of yourself after all. But this shift also comes with some issues.
The entire physiology of the cell changes. About 10% of all the proteins that the cell makes changes, which is about the same scale change you would see if a kidney cell suddenly decided it was going to be a white blood cell. And the whole cell takes on this behavior or phenotype, which makes it do bad stuff. Sometimes they act as agents of sterile inflammation. Sometimes they think they're bone cells when they aren't. Sometimes they take on other characteristics that are more subtle, but are still nasty. Why are they doing this? Typically, they're trying to attract immune cells to kill them and get rid of them. But your immune system is also made of cells, and it is aging. And so I sometimes liken this process to being on the phone to an insurance company, waiting for a quote. When you're young, you make a senescent cell. It's cleared almost immediately. It's like dialing the number and getting straight through. When you're my age, it's a little bit like being stuck in one of those queues where the body is basically saying, your call is important to us, please stay on the line. And so clearance fails, and the result is this kind of double whammy where you start to fill up with senescent cells, and they do really bad stuff.
So on a cellular level, we begin to pile up toxic junk. We also start to lose our helpers, stem cells. These are the cells in our bodies that have the potential to turn into different types of tissues so that we can repair and regenerate.
This isn't a phenomena where a cell simply becomes senescent. This is one where a very specific population of cells is lost or depleted. So if you think about the classic stem cell systems, which is basically in the crypts and the villi of your gut, the wavy things in your intestine, at the bottom of each of those little crypts is a stem cell. And those stem cells start to disappear as you get older. And one of the reasons they start to disappear is that stem cells are exquisitely sensitive to DNA damage. They have to be because they produce a lot of other cells. And so the whole purpose of a stem cell system is to produce lots of cells that divide rapidly and are thrown away. That system would be defeated if you had a stem cell that picked up a lot of different mutations. And so the way in which that's dealt with, certainly in the gut, is when a stem cell has picked up mutational events, it simply dies.
And so changes on the molecular level affect the cellular level, which impacts how the whole system works.
You need to think in terms of hierarchies. So short telomeres and damaged mitochondria are things you're going to find inside a cell. Senescent cells or depleted stem cells are things you're going to find inside a tissue. And defective tissues are things you're going to find inside an organism. And they can significantly affect overall organismal physiology.
Scientists like Richard are beginning to really understand what aging is. But that raises another question. Why does aging happen at all? At first glance, it doesn't make a lot of evolutionary sense. Why wouldn't we just go on reproducing forever and ever? Well, it's about turning it on its head.
There's the famous dictum, which I'm sure you've heard many times, nothing in biology makes sense except in the light of evolution. So when you're looking at what looks like a counterintuitive thing like aging, you need to start to think about why it might make evolutionary sense. Why do organisms grow old at all? Why don't they just carry on indefinitely? Because out in the wild, extrinsic mortality is extremely high. Chronologically old animals are really rare. That's because they get predated, they're prone to environmental accidents.
So in the animal kingdom, you're likely to reproduce when you're young, because you're probably not going to get old. And that leads to the first evolutionary theory of why we age, something called mutation accumulation. Back to Richard.
Consider a genetic variation that arises that will kill an organism, but only after it has reproduced. So the organism, whatever it is, reproduces at day 3, but this bad genetic variation that it's carrying won't do anything at all to it until day 5, when it'll kill it. And we refer to this as a fitness neutral variant because it hasn't affected the number of offspring that this organism is going to carry, and all evolution measures via natural selection is number of offspring. Maybe what we see in aging is just a grab bag of these fitness neutral traits that natural selection hasn't been able to get rid of. And that's sometimes called the mutation accumulation hypothesis.
The idea works like this. If there are gene variants that make an animal deteriorate in later life, but have no ill effects during its younger reproductive years, then natural selection won't remove them from the gene pool. Those genes still get passed on to the next generation, and so they build up over long timescales. And what if, on top of that, there are genes that cause problems in later life, but are advantageous when you're younger?
Imagine a genetic variation that makes you a better replicator early on in life. That will get very heavily selected for even if it's associated with bad stuff happening later. Because for most organisms, most of the time, there is no later on. And that's known as antagonistic pleiotropy.
But then again, maybe doing all this replicating also comes with a cost.
If you imagine having a pool of energy that you can allocate between fixing yourself, that is somatic repair, and making copies of yourself, which is reproduction, you can see straight away that dumping all your energy into either one of those two extremes is a bad deal. If I tried to dump all my energy into making copies of myself, I fall apart because I didn't spend any energy fixing myself. If I dump all my energy into fixing myself, I lose the game of evolution because I made no copies of myself. And so, in essence, and I'm doing a slight disservice to the elegance of the theory, in essence, what it shows is that almost all of the time, the optimum allocation of resources is towards a limited lifespan.
That theory is known as disposable soma. If you're likely to get predated, there's not much point putting your energy into surviving into old age. It's a question I put to Richard.
It's an interesting argument, would be my first thing. I would point out that there is no rationale that would allow you to turn around and say, we should not treat aging, but we should treat Alzheimer's disease or cognitive impairment. Let me explain what I mean. When senescent cells build up in my cardiovascular system, they give me cardiovascular disease. When they build up in my central nervous system, they give me cognitive impairment. And we call both of those diseases. When they build up in my skin, they give me wrinkles. When they build up in my hair follicles, they give me grey hair. And we call those natural changes. Do you find that logical? Since it turns out that the mechanisms driving the things we have chosen to classify as natural changes are the same as the things we have chosen to classify as diseases, there is no logical argument for not targeting that fundamental process.
And the thing is, this work to slow aging is already happening, with the aim to either make us live longer or help us to stay healthy as we head towards the mortal cliff edge.
The interventions that extend lifespan do so by improving health. And by improving health, they do one of two things. They compress the period of time you spend sick. Your lifespan doesn't increase, but you spend less time ill. Or they keep the period of time that you spend ill the same and extend the number of healthy years you get. And there is a cartoon strip that comes to mind. I used to be, in fact I still am, a big fan of Dilbert. Dilbert, as many of you will know, is a miserable sat-upon office worker in the cubicle farms. And the devil appears in front of him one day and says, I offer you a choice. You can have eternal high pay, but your work will be burned in front of you at the end of each day. Or you can have eternal low pay, but your work will be valued and appreciated. Dilbert looks at the devil and says, wow, these are both better than my current job. And that is kind of how I feel about the two outcomes that we're seeing from effectively modulating lifespan in other organisms. We get different outcomes, but both outcomes are better than what we've got at the moment.
How are scientists and billionaires attempting to prolong life?
It is funny, but all of these studies using molecular and cell biology on aging have showed that some very common sense advice actually affects some of the major pathways in aging. And that common sense advice is currently better than any anti-aging medicine on the market.
That's in our next Secrets of Aging special out on Thursday. Episode 2, Can we put off aging? And if we can, what does that really mean? This episode was produced by Madeline Finley. It was sound designed by Ian Chambers, and the executive producer is Ellie Bury. We'll be back on Thursday. See you then.
This is The Guardian.